Um, Good afternoon, everyone. Thank you for joining this UCAN Plus Physical Acoustics Special Interest Group webinar. My name is Sharam Tahazadeh, and I have the pleasure of introducing our speaker today, which is Professor Keith Attenborough. You've read his biography. He's been at the forefront of acoustic research for 50 years, since 1965. And in addition to what is there, he has rest of Europe, UK, and including Rayleigh Medal from Institute of Acoustics and others. And in a sense, there is no need to introduce him. His talk is on reflection and transmission of sound by vegetation. And I would like audience to keep the questions towards the end. There will be opportunity at the end to ask questions. So without further ado, I'll pass on the virtual microphone to Keith.
Thank you very much, Sharam, and thank you everyone for being interested in this webinar. I'm going to talk about reflection and transmission of sound by vegetation. Well, basically I'll review lots of work that's been done on this. But since vegetation normally grows in the ground, I'm going to start at the ground and work upwards until I get to the tops of trees, as it were. So I'm going to talk about ground effect first, and ground impedance models, and ground impedance measurement, effects of moisture and season, the influence of vegetation on ground impedance, sound absorption by plants, sound transmission through crops, foliage attenuation, sound transmission through forests, the influence of trees on coherence, the possible effects of planting patterns, an interesting forest edge effect, and then some conclusions if there's time. So first of all, ground effect. Many of you may be very familiar with this, but it's something I've worked on for a long time. And in case you're not familiar with it, it's basically destructive interference between sound that travels directly from source to receiver and sound that's reflected from the ground. Now, if the ground is porous, which it normally is if vegetation is growing on it, then the incident sound waves can penetrate, and they're subject to viscous and thermal processes during their penetration into the pores, and that means they get a bit delayed, which means that there's a phase change on reflection. And when added to the phase change due to path length difference, you can get destructive interference, and it's quite often at a frequency that's quite useful for noise reduction, surface transport noise reduction, and indeed there is an allowance for ground effect in prediction schemes for surface transport noise. So I'm trying to keep the number of equations I show to a minimum, but I have to show a few. So this is a classical formula for predicting ground effect, and it involves a spherical wave reflection coefficient, and that in turn involves a plane wave reflection coefficient. And the expression for the spherical wave coefficient includes a function called the boundary loss factor, and that in turn depends on a numerical distance, which I've given the symbol W, and that depends upon the angle of incidence and on the normalized surface admittance of the ground. And the surface admittance is the inverse of the surface impedance. So if you really want to predict ground effect, you need some way of predicting the surface impedance of the ground. And there are lots of ways of doing that. And in the midst of predicting outdoor sound, you don't want to use the most sophisticated models available for doing the ground impedance calculation, because you've got lots of other things to take care of. So typically, we try and restrict the number of parameters that are needed. A very popular model is the Delaney and Beasley model, and this was introduced in 1970 mainly as a way of characterizing fibrous sound-absorbing materials. And that uses just one parameter, flow resistivity, although sometimes you might refer to it as effective flow resistivity. Now, a Japanese researcher, Miki, modified the Delaney and Beasley model because he recognized fairly early on that it didn't satisfy the conditions that an impedance should satisfy. I'll go more into those later on. And so he modified the coefficients in that model, and so that's the modified Miki model. When I first started work on ground impedance a long time ago, then I was interested in the model originally suggested by a Canadian researcher, Donato, and that's called the variable porosity model. And that involves two parameters. One is the rate of porosity change with depth, or effective depth, and the other is flow resistivity. Miki had another go at ground impedance models, and he did produce something that's rather similar to other models that you see later on in the table, and that involved three parameters: porosity, flow resistivity, and structure factor, which fairly young we could recognize as something we call tortuosity in terms of the acoustical properties of porous materials. Zwicker and Coston in 1949 proposed a similar model involving these three parameters. And if you read Mawson Ingard's textbook, I assume people still read that, then that introduces the phenomenological model, which is a slight variation on Zwicker and Coston. Now, the European community, in its wisdom, supported development of models called harmonize model for predicting surface transport noise, and that refers to a model which it uses for porous asphalt, because porous asphalt is often used as a way of reducing tire road noise. And that was the Hamet-Beranger model. Actually, it was Jean-Francois Hamet that came up with it, and Michel Beranger claimed part ownership of it because he employed Jean-Francois Hamet. A model I'm quite fond of is of identical tortuous slit pores or cylindrical pores. And finally, the one in this table is Wilson's relaxation model, which in fact will feature in a new version of an American standard, which I'll talk about later. Also, because many grounds can't be characterized simply by these parameters, you sometimes need an effective layer thickness or an actual layer thickness, and so that adds the number of parameters. So here's a look at all these models. And as I say, the original Delaney and Beasley model was modified by Miki, who changed the exponents and the various expressions. And Didier Dragner in France also discovered that even the Miki's modification of Delaney and Beasley also didn't satisfy all the things that an impedance model should satisfy, so he did a further modification. Here is the variable porosity model. Here is the three-parameter Miki model. And you can see how that involves the porosity, tortuosity, and flow resistivity. And the Wilson model does also. Here is my favorite model, the tortuous slit-pore model. It's not as readily amenable to outdoor sound predictions as the other models because it involves the hyperbolic tangent function. However, that's also needed if you need to represent the impedance of the hardback layer, where the inverse of the hyperbolic tangent, namely the hyperbolic cotangent, is involved. So you need a way of measuring the impedance of the ground. You need this even when you're considering the influence of vegetation, because, as I say, vegetation is normally on some form of ground. And Sharam and I worked together with various other people on an American national standard for doing this. And essentially, it uses the difference between the difference in sound level spectra between two vertically separated microphones. And then you either fit one of the various models I've described to you before to the spectra, or you can do a direct impedance fit. At about the same time as this American national standard first appeared, there was also a Nordic standard, which does the same thing, but uses a different geometry. The advantage of knowing about the Nordic method is they've done rather more systematic measurements on ground impedance than any other organization in the world. And we've took advantage of their data, which was kindly supplied by Hans Jonasson. And we've been able to compare lots of models with their measurements. So in this particular example, if you look at the graph on the left, you can see that most of the models do a reasonable job of fitting the data. However, the same is not true if you go to a forest floor, which of course will be very important if you're trying to understand sound propagation through a forest. And there, the widely used Delaney and Beasley model fails drastically, even when it's in its hardback layer form, whereas other models do work. I haven't talked about the Taraldson model, and I won't talk about it. But you can see that one reason why a simple model won't work is because forest floors can have a very complicated structure, ranging from dead branches to decaying leaves to decayed leaves to the underlying soil. So it's not surprising you can't get away with a very simple model for those. However, both the slit-pore and the Wilson models have been found to have pretty good agreement with these kinds of forest floor data. A recent study has been done by my co-author of the book, Predicting Outdoor Sound, Timothy Van Rent again, where he did lots of measurements on different forest floors. In this case, young ones, that is, the forest floor, so to speak, would not be the same as you might find in a more mature forest, because there's been less time for leaves to decay and so on. But there are interesting things shown here. The Delaney and Beasley layer gives a much bigger error. The vertical axis is the error in trying to fit vertical level difference measurements, vertically separated microphone level difference measurements, compared with the other models. In this case, he compares with slit-pore layer and Zwicker-Coston layer. And the other interesting thing is that they did measurements where they removed all the decaying leaf litter. And I'm afraid Delaney and Beasley didn't do much better with the underlying soil than the other models. So if there's one lesson so far, please don't use Delaney and Beasley when you're considering propagation through vegetation. Since this is a physical acoustics seminar, it's very important to point out that the conditions I said should be satisfied by a surface impedance are the conditions of physical admissibility, and they can be expressed in lots of different ways. But the simplest way is in terms of the real part of the complex density. In describing the acoustics of a porous medium, you need a complex density and a complex compressibility, and a simple test of whether or not the real part of the complex density goes negative, you can't have a negative density, is being used here to show that unfortunately the Mickey models don't work, as and neither do the Delaney models. Delaney and Beasley model, if you go to a low enough frequency, here I'm plotting against the horizontal axis is frequency divided by flow resistivity. So in the case where you've got a flow resistivity of 200,000 Pascal seconds per meter squared, which is quite a high flow resistivity, might be typical of a soil, then you get departure, or you get negative going values for the real part of complex density below 2 kilohertz, which is, of course, an relatively important frequency in terms of predicting propagation, audio frequency propagation through anything. And if you went to a tenth of that, then you'd be talking about an even higher frequency below which this real part not being negative is not satisfied. So let's talk more about vegetation, since I've spent 15 minutes on ground effect, whereas I'm really supposed to be talking about vegetation. Vegetation reduces the flow resistivity of soil. And that's because the growth of the roots, if you like, loosen up the surface layer of the soil. They make it more porous and easier for sound to move backwards and forwards through the surface, hence the reduction in flow resistivity. And we found this when we were doing measurements of propagation through crops, because I had a student who meticulously removed all the stems from an area of the crops, and we measured the impedance of the soil underneath the crops. And we also measured the impedance of the soil outside the crops. And we could see quite a big difference in the fitted flow resistivities. In fact, there's up to a factor of 10 difference caused by the presence of the crops. And a long time before we did these measurements, there was a group in the Netherlands that were interested in outdoor sound propagation, and in particular on botanical aspects of it. And they measured the flow resistivity directly, rather than fitting acoustical data. And they measured it on the soil, bare soil without any vegetation, and on the root zone that's caused once you have vegetation. They extracted samples of the root zone. And you can see again how the flow resistivity is much higher outside of the root zone than it is within it. So we're gradually working upwards, and so we're now interested in the plants that are growing on the soil. And a series of very nice measurements have been done by a group led by Kirill Horoshenkov as part of a project we worked on together some years ago. And he measured the absorption coefficient spectra of the soils in which plants were planted, and also the plants themselves, and also the combination of the plants and the soil. And he had two types. He looked at two types of soil. One was fairly compact, and the other was a substrate that was used in, at that time, living walls. Unfortunately, the company that made these living walls no longer exists, but still green facades still exist, and this would be the kind of substrate that's used in them. And although as I described, using the Mickey model is not a good idea, Kirill nevertheless used it and got quite good agreement using using it. And for the different types of soils, the low flow resistivity one, the substrate as it's called here, and for the much higher flow resistivity one, the clay-based here, he could get good results. Also, Kirill noticed the very big difference between whether the soil is dry or the soil is wet, and this is true of both cases. The lower flow resistivity soil is less affected by a given moisture content than the high flow resistivity one. Some other people have done work on the seasonal effects on ground impedance, which is important when we come later to look at propagation through vegetation, since there's a seasonal effect there too. And it's not just the leaves, so it's also the ground. So here with this French group looked at, well, they actually looked at 3 different surfaces. One was an artificial grass surface, so I'm not showing those data here, but we're now looking at, on the graphs on the left are of the surface impedance, real and imaginary parts, and you can see how they change between the means change between summer and winter. And they change rather more for the relatively compacted soil, which is what you would find in a typical lawn, compared with the less compacted meadow. And here is the change shown in terms of flow resistivity values and their standard deviation, summer versus winter, and the effective layer thickness values, summer versus winter, for 3 different types. There's the 3 different types of ground that they looked at, but we're most interested in the grass and the natural in both cases. So the flow resistivity of the grass, which is the lawn, has gone up as a result of during winter versus summer, and the same is true of the natural grass, but to a lesser extent. Natural grass being the what I previously referred to as meadow. Back to Kirill and the plants, and Kirill also found that he could model the absorption of the plants themselves and the plants on soil using this Mickey model, which is a model for the acoustical properties of a porous medium. And this shows the various good fits he could get, both when they're on the low density substrate and when they're on the high density soil. And you're getting much higher absorption coefficients on the substrate because the substrate itself offers a good absorption, whereas the same is not true of the high density soil. So, intriguing idea that you can model plants or the acoustical properties of plants as though they're essentially porous materials. Kirill pursued further in deriving various of the parameters you need for describing plants as a porous material in terms of sound absorption. And the interesting thing he looked at was tortuosity, which is one of the parameters that's important in describing acoustical properties of a porous material. And he found that this depended on the leaf orientation. Basically, the flatter the distribution of leaves, the bigger the angle of theta, then the I think it's I can't remember which way around it is. I think it's the higher the tortuosity. So now back to our measurements through crops. We're working our ways up because Kirill's work was about low growing plants, and I guess crops are kind of intermediately growing plants. And we've looked at propagation through 3 different conditions. An almost harvesting time, August, and a vigorous growing time, May, and vigorous growth having occurred time, June. And if we look at in this case now we're looking at horizontal level difference, that's the difference between a microphone over here and a microphone over here. And in this horizontal level difference, we can still see a ground effect. And we also see a very high frequency attenuation. And when the range is increased, then we can still see a ground effect, although it's less, and we see even more high frequency attenuation. So if you can see the different curves, the red and the blue, which correspond to the higher plant densities, and there's much less ground effect in those than in the lower plant density. And the high plant densities result in the higher attenuation at high frequencies. In this case, it's above 2 kilohertz. We had a go at modeling the high frequency attenuation by saying that it was the result of multiple scattering by the stems of the plants and also by the leaves, I guess, and using a theory developed a long time ago, we were able to come up with a relationship between what we call the filling fraction, which later on I'll be describing in terms of leaf area density, and the effective flow resistivity. Not surprisingly, the more stuff there is there, the higher the flow resistivity. The presence of the stems and the foliage in crops does one other thing. Well, it does the thing that I talked about in terms of reducing the ground effect. It reduces the coherence between the direct sound and the ground reflected sound, which you need for getting that soft ground attenuation. And when we first looked at this, we modeled the effect as though it was the same as you get from turbulence in the atmosphere. So if you like, it's a kind of the stems and the foliage act as a kind of frozen turbulence. And this is how we can calculate that effect. And so when we do the fairly complicated task of adding ground effect, incoherence due to scattering effect, and a sound absorber or visco-thermal foliage attenuation, we find we can get a pretty good fit to our data. Of course, you wouldn't want to do all of that every time if you were trying to predict propagation through crops. So what we also found was if we adjusted the parameters for the ground and for the foliage attenuation, then we can also fit the data in a much simpler fashion. And that's what we did when we looked at sound attenuation through hedges. And this is showing a hedge on the Open University campus in Milton Keynes, next to the tennis courts. And there was a convenient gap, so we could do measurements in the gap, and we could also do measurements behind the hedges. And when we looked at various cars, pass-bys, we could see these kinds of results. So in the gap, we got this result, and behind the hedge, we got these results. So this includes both data and a prediction using the ground effect plus the foliage attenuation effect. And we can get pretty close to these data, but it just shows that the hedge is not giving very much in terms of insertion loss, but nevertheless it's giving some. So we're going higher up still. Now we're now into woodlands. And many years ago, early 1980s, I had a student, Margaret, who did lots of measurements in different types of woodland. And this shows some of the results, but we're plotting now the level difference between, or the horizontal level difference between a reference microphone near the loudspeaker source and the microphone some distance away, in this case 72 meters away. And we're plotting the negative of what we plotted before. So the ground effect appears as a peak, low frequency peak. And there are lots of things we can see here that there's a difference between summer and winter. And there's a difference between the summer maximum and the summer minimum, both in terms of the ground effect and also this higher frequency effect, which I've already told you we're ascribing to the effect of foliage. If we only looked at the foliage and just looked at these particular three woodlands, then we can see more clearly how the foliage attenuation differs between winter and summer in the deciduous trees, and between the different types of trees. So the spruce and the mixed conifers are not deciduous. So the spruce was kind of in between the minimum and maximum attenuation in the deciduous forest. But the mixed conifers, by the way, I've been talking to people from forest research who are measuring the density of foliage by checking how far you can see through it. That we did that as well. We had a student who dressed up in a white tracksuit, and we measured the distance beyond which we couldn't see the student. There are more sophisticated ways of measuring foliage density now. So how do we model the effects of foliage? Well, Donald Ayler from Connecticut in the States did lots of measurements and published lots of work about the dependence of the sound attenuation through foliage on the characteristics of the foliage. And he identified the foliage area per unit volume, which I think is related to leaf area density, the length of the propagation path, and the mean leaf width as the important parameters in determining foliage attenuation. He also shows a curve based on plotting these parameters, without explaining what how he got this curve. I guess it's kind of best fit line he's done. Doesn't give an equation for it. But we've used various equations for a curve that fits these data. This is a nice empirical one suggested by a Dutch researcher, Kees Harman. He suggested it after he noticed several difficulties with the formula we had been using as a fit. Donald Ayler said that neither the quantity nor quality of the attenuation can be accounted for by viscous and thermal dissipation at the plant surface. Well, we've already found that Kirill Horoshenkov could fit most of his measurements of the acoustical absorption by plants, assuming that you could treat them as though they're porous absorbers. And that accounts for everything that would be going on in terms of viscous and thermal dissipation. And I've also had a go at fitting these same data using my favorite tortuous slit-pore model. So I don't think Ayler was correct. You can model the attenuation, acoustical attenuation through foliage as though it's through a porous material. Of course, it's a very low flow resistivity porous material, and very high porosity and a relatively low tortuosity. So here we're plotting lots of different foliage attenuations and distinguishing between the different types of things. So corn, or crops, I would say in general, will always give you the highest foliage attenuation. And the spruce plantation that Margaret did her measurements in offers the lowest in this set. But here I've generalized to lots of different things and given you the best fit values of leaf area per unit volume, or leaf area density, and mean leaf width, and also the parameters that fit using the slit-pore model for these various things, various types of vegetation. So I did work also a long time ago with Willebrord Hausman in the Netherlands, who was doing measurements in a Dutch polder forest. And what we found was that we could fit these data obtained. These are data at 100 meters of propagation through this forest and at different microphone heights. So the lowest microphone shows the biggest ground effect. Now we're plotting something called excess attenuation. It's not the level difference between microphones. It's the attenuation in excess of what you get from wavefront spreading and air absorption. And the ground effect shows up like this. And the foliage attenuation shows up in terms of the high frequency loss. And if we look at the different microphone heights, we find that we have to use slightly different ground parameters and certainly different foliage attenuation in order to fit these data. And whether it's by luck or judgment, it turns out that the 4.5 meter height is fairly close to the published expected maximum foliage density in such a forest. So here is my reference for saying that. And that's where we had to assume the biggest effect due to foliage in terms of incoherence, and the biggest effect in terms of foliage attenuation in order to fit these data. There is a Nordic prediction scheme, Nord 2000, which attempts to predict the attenuation through forests through this rather complicated formula involving a coherence factor and also a coherence coefficient and also a coherence factor, which is the fraction of coherent sound transformed into incoherent sound. And these people, Torero et al. In Spain, did some measurements to check out this model, and they didn't find particularly good agreement, although including the attenuation due to soft ground effect plus scattering by trees did make some difference to the prediction. There are various reasons, I think, why they couldn't get particularly good agreement. And one will be that they were using the Delaney and Beasley model for representing the acoustical properties of the forest floor. And I hope you'll remember that I think that's a bad idea. So, before we were trying to take account of the incoherence due to scattering by trees by assuming that the trees behave like frozen turbulence. Well, my good friend Vladimir Ostachev has done a much better job of this and worked out what the effect on coherence in the ground effect should be of scattering by trees. And he's come up with these results. And you can see how the coherence factor he's come up with would vary with the different types of trees that Torero et al. Measured in. And here are the fits we can get. Actually, we don't do a lot better than Torero et al. Did. And Vladimir is very miffed about that, but there we are. But nevertheless, we are showing that what you expect the effect to be. One of the other differences between the Nord 2000 and the Ostershef coherence coefficient is the Ostershef one takes into account the height of the trees, because he used scattering by finite length cylinders in order to come up with it. One of the very interesting things that Timothy van Rentegem did in the context of our Hosanna project was how you could design a tree belt to give you good transport noise reduction. And he used a numerical finite difference time domain model to do this. And I'm just showing you the kind of results he got. So he looked at lots of different planting patterns, including missing out rows, which will be something I'll talk about again in a moment. And he also looked at different trunk sizes, trunk diameters, and different regular arrangements. So this is showing rectangular arrangements, but also he looked at triangular and face-centered square and so on. And he got these various predictions. So what is interesting is from this 15 meter wide belt, it is, yes, you could get up to, well, more than 8 dB in terms of the insertion loss, of which 3 dB was contributed by the forest floor, using a realistic model for the forest floor. So something related to leaving gaps in the planting pattern is this interesting non-reciprocal forest edge effect, which was found by Michel Sweringen and colleagues in the States. They were doing measurements using a propane cannon, and they had 2 source locations for it. One was outside the forest and one was inside the forest. And if we look just at the difference between microphones either side of the forest edge here, then you get different results depending whether the source location is inside the forest from when it's outside. So that's propagation from the source outside into the forest. And this is the propagation between the same receivers when the source is inside. So the propagation is outside. And as you can see, there's much less attenuation going from inside the forest to outside than there is going from outside the forest to inside. Very intriguing. And someone could write a paper if they can explain it. But the interesting thing from the point of view of using forests for noise reduction is you can deliberately introduce breaks in a forest to exploit this effect. So I'm hoping I've left you all with enough time to ask me lots of questions. Whether or not I can answer them, I don't know. But here is a quick summary of what I've talked about. Vegetation alters the acoustical properties of the ground. Vegetation, propagation through vegetation then depends upon soft ground effect, scattering by stems and foliage, or trunks and foliage, or branches and foliage, and visco-thermal effects at the foliage, which are similar to those you get in a porous sound-absorbing material. The soft ground effect is reduced the higher the stem and foliage density. On the other hand, the foliage attenuation goes up, and it depends on leaf surface area per unit volume and mean leaf width. The attenuation through crops, trees, and hedges can be described just in terms of soft ground effect and foliage effect. The influence of the trees on the coherence on which the soft ground effect depends on plant density, and according to Vladimir Ostashchev, also depends upon the mean vegetation height or mean tree height, which is only looking at forests. You can increase the attenuation of a tree belt by using almost regular planting, high trunk basal areas, deliberately introducing breaks if you've got enough width to do this, and dense understory. The denser the foliage, the more foliage attenuation you'll get. You can get from a 15-meter wide tree belt, including a forest floor effect, you can get about 8 dB reduction for transport noise, road traffic noise, that is. The edge of a forest has a non-reciprocal effect, which to date has not been explained. And there's lots of scope for further research on acoustical characteristics of ground surfaces and non-foliage attenuation. Thank you very much.
Thank you very much, Keith. This was a very comprehensive review of propagation over and through vegetation. Thanks very much. We have a few minutes for questions. There is already one question that's been typed by Gordon Hunter, and I read it to you. How can you control the factors such as ground moisture level differences? Perhaps the height of the vegetation is relatively easy to measure and control, but possibly less so for varying moisture levels.
Yes, but if we're interested in propagation through forests, forests and indeed through crops, then the soil moisture effect is not as big as if you had bare soil. So although you can't control it, it has relatively little effect. I hope that answers the question.
Thanks. There are a couple more questions typed in, and you can also raise your hands and I'll let you speak. Antonio Filippone asks, what is the noise source? How is the frequency controlled?
Okay, so for most of the measurements I was talking about using a loudspeaker source, and sometimes it was a dual speaker to get a good frequency range. For the measurements of ground impedance, then various standards recommend using something that is close approximation to a point source. And typically we're interested in the range between, shall we say, 100 hertz and a few kilohertz. But in terms of foliage, if you want to measure foliage attenuation, then you need to be able to measure to higher frequencies. So that depends again on the frequency response of your loudspeaker and on your measuring equipment.
Yeah, thanks very much. As you saw from the pictures, the measurements we did for the ground impedance are shorter range at these conical shape sound sources, which mimic a point source, basically. Question. Neil Jones asks, what advice would you give to an urban school wanting to reduce noise pollution from a nearby road?
Yes, well, I'm assuming that there isn't much space around an urban school and that roads are fairly close to the property. So I think most of the effect you could get would be on your building design. Rather than use of natural means. But you can have a combination of artificial and natural means. So if you haven't already got double glazing for the noise exposed windows, then you need to get that. And you can also get vegetated barriers, which do quite a good job. I haven't talked about those at all, but the Hosanna project also looked at low height vegetation barriers. If your nearest noise source is road traffic, then that source is quite low down. So a low height barrier can do something.
Thanks very much. Couple more questions. Gordon Hunter again, follow on from his question about moisture. Is that I guess the situation might be different for remote sensing applications, for example, using drones. And some of his colleagues work on that sort of thing. Can't see what effect remote sensing would, what difference remote sensing would have.
Well, I'll talk about two things I know in terms of remote sensing. Actually, the Nordic standard, or the Swedish Building Research Institute, when he was looking at ground effect, looked to see whether or not you could use images from satellite sensing, satellites, to determine ground impedance. So I don't think that was very successful. I think you've got to do an acoustical measurement. But the other thing about remote sensing is that, I was talking about the measurement of foliage density. Well, that's often done using LiDAR. So it uses optical scattering as the basis for determining the foliage density. So that may or may not answer the question, but it's the only two things I know about remote sensing.
Thanks. I think Gordon meant drones rather near.
Oh, right. Well, the propagation of
propagation.
drones. Okay, so yes, if you're interested in reducing the impact of noise from drones by natural means, then yes, presence of vegetation will do something in terms of reducing the reflection from the ground, even though drones are fairly high up. And I mean, various aircraft noise prediction schemes take into account the influence of the ground. So as long as the receiver is receiving the noise at a fairly grazing angle from the flying object, then ground effect will be important, and so will be the presence of vegetation.
Thanks. Questions keep coming, so let's. Claire Woodall asked, do you think the reduction of the frequency of the sound wave is key?
Well, it depends what you're trying to use it for. I know Claire is interested in seeing what the various vegetation uses buffer near to road traffic noise can be. And so, I mean, essentially what I've tried to convey is there are two frequency ranges in which tall vegetation can be having an effect. Now, if it's young tall vegetation, then it won't have had enough time to create the soft ground effect you can get with a more mature planting. So the main reduction will be to the high frequencies through the foliage. And so the reduction of, for example, road traffic noise won't be as good as you would get from a mature tree belt, because of the fact that that will also give you soft ground effect.
Thank you. An anonymous attendee is asking if you can recommend the introductory text for learning about modeling visco-thermal losses using complex sound speed, density, and compressibility. I suppose this is a good opportunity to recommend your own book.
I could recommend my own book, but in fact, if you're interested just in modeling sound absorbing materials, then you can't go far wrong with the book by Allard and Atala, although I prefer the first version by Jean-Francois Allard of his text on sound-absorbing materials.
Right. I'll try to type in the Allard names. J.F. Okay.
So there's room for another book, which either Thomas Zielinski or Olga or Rodolfo or all of them could write.
I'm sure. Final question from Ian Thompson, which is, I was going to ask a similar question, but is there a reason to expect the reciprocal effect from the far edge effect? Why is
yes.
a non-reciprocal effect surprising?
Okay, well, I guess I'm thinking in terms of transmission loss. So it shouldn't matter which direction you go to get a given transmission loss, should it? I mean, the one thing we know about the edge of the forest is it will have a higher foliage density because there's more light there than anywhere else. But nevertheless, I would expect transmission in either direction to give you the same insertion loss. But there you go.
Can I ask a related question, which is that I can think of two mechanisms by which the propagation on either side would be different. One is that with the source inside the forest, you will get, by scattering, you will get multiple effective sources of sound coming from multiple directions, effectively. And the second is that because there is attenuation inside the forest, in effect, the forest medium is an effective medium with different complex sound and complex sound speed and complex density. Therefore, there will be an impedance mismatch between open air and forest medium, and you would get different reflections, impedance mismatch effects for sound coming in different directions. It would be nice to be able to calculate that, but
yes, well, I think possibly that your explanations are right. Yes, you could come up with an effective medium for propagation inside the forest.
Yeah.
And so what you're saying is you're getting more diffusion within the forest, and you're getting a refractive index. You're getting refraction too.
Yes, effectively.
Yeah.
Right. Are there any more questions? I can't see anyone raising hand, and Claire and Gordon say thank you very much. And if there is nothing else, it leaves me to thank you, Keith, for your interesting talk, and then thank the audience for joining us today.